Thank you, Eduardo. Good afternoon to everybody. Useless to say, I cannot start my talk without first thanking deeply the organizing committee, all the members of the organizing committee for giving me the opportunity to give this talk. So, as you read from the title, I'm going to talk about a very natural structure of the polynomial rings over G L infinity. Polynomial rings, I'm considering polynomial rings over the rational numbers because I don't need anything more. Indeed, I could even work over the integer, but I avoid questions that could have no relationship with the talk. And so, GL infinity, what is this? Start to think to very huge matrices where each entry is labeled by two index, ij, which runs over the integers from minus infinity to infinity. And that has all the entries 0, but 1 in a given position, ij. And then you take the linear space generated by all these elementary matrices, which have only 1 in one position and 0 elsewhere, and then you get GL infinity. It's just the generalization of the algebra of all n times n matrices with entries in a given field. And you can easily imagine that this space, this vector space over the rational, in the case I'm concerned with, is a Lie algebra. So I want to show you that on the behalf of my collaborator, Paran Saleyan, friend and collaborator who works at UNESP of San José do Rio Preto, I want to show to you that there is a very natural structure of polynomial rings in finitely many indeterminates over the Lie algebra of the infinite matrices, which have, let's say, all the entries 0, but finitely many. And then I go forward with my slides. Oops. Yes. So I deeply regret that Professor Aronsimis is not here, who does recognize in this audience this picture. This is the picture I took from my windows, from the windows of my room hotel in Maragogi in 1908 during the second ALGA meeting. And you see? And as incredibly it may sound, I took this picture. It's not a postcard. 98. With
88.
Oh, I'm sorry. I'm sorry. 98. And this was the ALGA team at that time, 98. I'm sorry. This is the ALGA team at that time. And look how ALGA grow up along the times. So that was just an introduction, Amarcord. So here I started with an outline of the talk in order you know what you have to expect from it. ALGA pictures, we already did. Then I started with some motivation, a background. I will state the main result, and I will give you a sketchy idea of the proof. Of course, it's dutiful to present at least a sketch of the proof, but in the slides regarding the proofs, there are only two ideas which are really important, if they are important. The rest, of course, at the end of the talk, everybody is slightly tired and may miss some technicalities. But the very important points are 2 and 3. To understand the motivation, the background, and the main results. So, motivation. The motivation comes during our reading of this very inspiring and beautiful book. It's a book by Professor Katz, Professor Reiner. The first edition was published in 1987. This is a new enlarged edition with the collaboration of Professor Natasha Roskovskaya, which works at Kansas University, and where there is a new part regarding vertex algebra. And in this book, but now the slides refers to the previous edition, there is at page 53, I guess, this proposition 5.3. These, you see, the EIJ you see there are precisely this huge infinity times infinity parameterized by the integers elementary matrix which have all the elements 0 but one the position I and j. And you see that here there is a generating function. There are two formal variables, u and v, and this expression is what is called the vertex representation of date Jimbo Kashiwara Miwa, and it was obtained in the context of infinite dimensional integrable systems. Okay? And we are concerned in our talk especially with the arrowed operator gamma uv. In my talk, I apologize, u will be called z and v will be called w. But by the way, gamma uv is a vertex operator. It's called, I will not enter in the details why this is called the vertex operator. It has to do with some natural structure of vertex algebra carried from some spin representation of a canonical Clifford algebra. But by the way, this operator acts on this ring. B is the ring, at least in the book I'm concerned with. B is the polynomial ring in infinitely many indeterminates. And you take B and consider polynomial in Z minus 1. And so those operators, you see there is the second exponential in the formula 533 is something which looks like quite nasty because it is the exponential of infinitely many partial derivatives. Okay? And it acts over polynomials and also. Then this generating function says you this. If it's true that the polynomial ring in infinitely many indeterminates has a structure over GL infinity, then you must know what is the meaning of taking a matrix Aij, which has all 0 but 1 in one position, and you take this matrix, multiply it by a polynomial, you want to know what is the result. And then this formula says, okay, it is simply you multiply the polynomial for this function, and then you just consider the coefficient of ui vj to find the results. That's the idea. But then my collaborator and myself asked ourselves if these things has a counterpart in a finite dimensional context, because the reading of this page suggests some natural questions. For instance, let's start by the model, the standard model of a vector space of infinite dimension, the vector space of polynomials in one determinants with q coefficient. Then the R exterior power of V, you see now R is a finite. I had to tell you that this action is induced by an action of GL infinity over infinite dimensional exterior power. So what does it mean wedge infinity over V infinity? This I forgot, but then we want to study the case when we consider only finite exterior power of V. And wedge RV is a GL infinity module. I will explain this in the next slides via the traces of endomorphism. You take an endomorphism and you can define the trace of an endomorphism. Moreover, there is an isomorphism. This is not very well known. At least, I think that at least it's not very well assimilated, that the R exterior power of a vector space is the same as a polynomial ring in R indeterminate. Here the indeterminates are called E1, E2, ER, but they are exactly the same thing. I want to tell you something more, that philosophically, wedge RV has no reason to exist unless you don't think inside its exterior algebra. Only inside the exterior algebra it comes to life, because otherwise, considering the first member or the second is exactly the same. And for our students, probably, the first member is easier to catch. Anyway, there is this isomorphism that to provocate people from representation theory, I call the BF, which means a boson fermion. This is what we call the finite dimensional boson fermion correspondence. And then the question is, what does the induced action of GL infinity look like? Why not consider even a simpler question? Because you see, I consider V a vector space which has infinite dimension, but why don't consider a finite dimensional vector space? Because if V has dimension n, then wedge RVn is naturally a GLn module, not a GL infinity. GLn is something which we can control better because it belongs to our first mathematical experiences. And what is the ring that wedge RVn is isomorphic to, and how does its induced GLn structure look like? So I want to find a ring which is isomorphic to wedge RVn and to study the action of this ring or the action. Now, somebody of you may say, I know what is that ring. It's the universal decomposition algebra of the polynomial xn as the product of two polynomials, one of degree k and one of degree n minus k. That's true. That's true. But it's useless from our point of view. It's very important to understand what is the ring, the isomorphism of this ring, which is more useful for our goal. And so, to start with, I start with Vn, Qx polynomial modulo xn. I consider V will be a short for V infinity. And for typographical reason, I will denote the basis element x to the I by Bi. Then Bn is a basis. I'm considering a vector space which is the linear space of B0, B1, B2. But you see, the index varies from 0 to n. And from now on, my n is free to be finite or infinite. And I denote by beta n the dual basis of Bn. And Eij is precisely the matrix which has all 0 but 1 in the position Ij. In fact, this you see, if you take that matrix and multiply by the kth element of the basis, you get delta jk bi. For example, if we were in the endomorphism ring of V3, on a space of dimension 3, E11 is this matrix, E23 is this matrix, and if I multiply E23 by B3, I get 0, 1, 0. The congruence symbol is because, I'm choosing an isomorphism to express BI as a canonical basis. Okay? Then for all n, which can be either finite or infinite, let GLN the space generated by this elementary matrix, which is contained in the Lie algebra of endomorphism of Vn. Why say I contain? Because I'm not excluding that n is infinity. Otherwise, they coincide. Okay? And this is a Lie algebra with respect to the usual matrix commutator. What is the trace representation? For all integers, now n may be either finite or infinite, and for all integers between 1 and n, the map GLN wedge times wedge RVN to wedge RVN, defined this way, that is, I take a monomial of the exterior algebra, or the exterior power, and I want to decide what is the matrix multiplied by this monomial is the trace. The trace, this is, you know what is. You take A and distribute it to each factor, plus figure out the last factor, last exterior factor. This is the trace representation. Then this trace representation makes wedge RVN into GL module. As a module, as a Lie algebra, you must check this. It's an easy check that this makes the R exterior power into an algebra, into a module over the Lie algebra of the n times n matrices. But then it appears BRN, which I call the alter ego of wedge RVN, which is, in a sense, I like even more. I define a polynomial of degree R, I fix R, and E1, E2, up to ER are formal variables, are indeterminates. And then I consider other indeterminates, infinitely many indeterminates, HI, H0, H1, H2, infinitely many of them, and there is a vector space isomorphism. If n were 4, R2, wedge 2C4, there is an isomorphism of this exterior power with BRN. BFRN is a new provocation, boson-fermion correspondence Rn. And the isomorphism is this one. You see, I have the polynomial ring infinitely many indeterminate E1, E2 up to ER, and then H1, H2, infinitely many indeterminate, but the E1s are finite. And then I consider the quotient. That this can be computed. This can be computed. You see that BRN is isomorphic to this, where you see ERZ and HRZ minus 1. That relation means, is a short to say that this is the ideal generated by all the coefficients of the equation ERZ times HRZ minus 1 equal to 0. It means in those equations there is 1 equal to 1, and then all the coefficients of Z must vanish. This in particular says that the first R elements of the sequence of the H1, H2, up to HR are algebraically independent, but HR plus 1, HR plus 2, and so on, because of the first relation, are algebraically dependent and are explicit polynomial in E1, E2, up to ER. And then we have some relation. And this can be written as, more simply, as the quotient of BR over HN minus R plus 1 up to HN, which are those relations. I eliminate where BR is a short for BR infinity. I take n going to infinity. If n going to infinity, I have not those relation anymore. And, well, no, I have those relations, but I'm not considering ERZ, HRZ minus 1, which is what I needed to cancel the H1, H2, the sequence from the presentation. And this is simply where BR is just the polynomial ring in R indeterminates E1, E2, ER, modulo Hn minus R plus 1 up to Hn. This is, remember that each n minus R plus 1 up to Hn are explicit polynomial expression in 1, E2 up to ER. So they form really an ideal in the same polynomial ring. Okay? And there is an isomorphism. The last presentation, QE1 up to ER modulo the relations, is isomorphic to wedge R Vn. This can be seen really algebraically, by hands. You don't need to know anything. But let's give some geometrical proof, just to be convinced that it is true what we are talking about. And the proof is this. But wedge R Vn is isomorphic to the singular homology of the Grassmannian. And last is just the presentation of the cohomology ring of the Grassmannian. And then, though that vertical arrow is just a Poincaré duality, where you are identifying E1 up to ER with the Chern classes of the tautological bundle. And the H are either the Segre classes or the Chern classes of the universal quotient bundles over the Grassmannian. So this is the proof that wedge RVN is indeed isomorphic to the ring I depicted in the last line. Okay, so the goal, then BRN, look, if it's true that wedge RVN has a GLN module structure over as a module structure of the Lie algebra of GLN, then the same can be transported over BRN. For instance, if B1 would be the polynomial ring in one indeterminate, so it is isomorphic to V. And the isomorphism is what? I take the high power of E1 and I associate BI, including this induces the GL infinity structure. You see, I multiply the matrix which has 1 in position ij for the kth power of E1, and I got that expression, just translating from one side to the other. So the goal is to describe the pullback on BRN of the GN structure of wedge RVN. An example, a challenge, and a hint. The example is B24. B24 is that ring. The polynomial ring in 1, E2, and H3, H4 are explicit polynomials of degree 3 and 4, weighted degree. We are giving degree 1 to E1 and degree 2 to E2, weighted degree. And so if you do some computation, that is clearly the presentation of the cohomology ring of the G24, you see that that ring is freely generated by those 6 polynomials. And then, if we would like to compute the product of a general element of that ring for the matrix E1, 2, what do? You use the trace over wedge 2Q4, the trace. No? You take that matrix and then you translate via the isomorphism and you find this polynomial as something really computable. If I give you a polynomial, I give you a matrix, you first let the matrix acting on the exterior power, and then you translate over the ring. It's very computational, everything is very explicit, but the challenge is find a formula for this. Okay, give me a formula. I take any polynomial and I multiply by eij. What is the result? The int is asking yourself a simpler question. Look for an expression for this generating function. Look, a generating function is fine. I'm sorry that there I wrote ij bigger than 0, but I want to say that ij range from 0 to n minus 1. So that is a finite sum. It's just a finite sum if n is finite, but our presentation is uniform now. N may be even infinity. And this generating function takes a polynomial and sends it to a formal power series. Well, in this case, would be a polynomial. You may ask me why I put 2 brackets in front of z, because n for me may be infinity. So, okay? So that the product of a polynomial by a matrix, elementary matrix eij, is just the coefficient of zi w minus j in the expansion of that expression. Then I want to find a formula for EZW we want. And it is well known that Brn, even if n is infinity, is a vector space which has a basis, and the basis is parameterized by partition. I mean, every polynomial in Brn, which is the quotient of Br, polynomial ring in E1 up to Er, can be written as a finite linear combination of sure polynomials, where delta lambda HR is this matrix. You see, I put in red the H lambda 1, H lambda 2, H lambda R corresponding to the partition, okay? And then there is a rule. You increase the index going downstairs, decrease the indices going upstairs. And you get a well-defined element of BR. I should have written BRN. I'm sorry. For example, this polynomial, E1 to the 4 minus E2 to the square plus E1 is equal to that linear combination. You just need to get used to this. This is not something we invented today. This is in the book by MacDonald, for instance, on symmetric function. Okay? So this is a very well-established technology. This is an exercise. And you see that you can express P in function of the H, expanding the determinants. And you see that also appears on H4. But this H4, if R equal to 2, is algebraically dependent from H1 and H2. So I want to use heavily the fact that this ring Brn has a basis parameterized by partitions, and this is the basis of the famous sure polynomials. And then I want to consider two maps. I'm sorry, here starts the technique. I want to define two maps, sigma minus z and sigma bar minus z, which goes from Brn to Brn z minus 1 polynomials through these equalities. Look, if I want to know how these maps acts, I let it acting on a basis. I take a basis element, delta lambda HR, and I'm claiming that this is the same. I mean, I'm defining this sigma minus in such a way that it passes through the parentheses, acting where on HR, which means I apply sigma minus z to each I. I apply sigma minus z to H1, sigma minus z H2, and so on, okay? Yes, but what is sigma minus? I didn't say it to you. And this is the same. For the sigma bar, I use the color to see the action, where where the only thing we know to know this definition is that is how the sigma minus acts on the H's. And this is the action. You cannot familiarize with this action so very rapidly, but then I have an exercise for you. Sigma bar minus z, it means applied to H3, is H3 minus H2 over z. Diminish and divide by z. Sigma minus without bar, H2 is equal H2 plus H1 over z plus 1 over z squared. Is exactly the meaning of the formula I showed in the previous slide. And the sigma minus z delta 2 1 HR, it means sigma minus z. I forgot the definition of sure polynomials. I wrote that for you. Is that a determinant? Okay? And then the definition says that you must compute the determinant of the sigma minus applied to each element. And then now use the exercise. Okay? Using the exercise, you see that H2 goes to H2 plus H1 over z plus 1 over z squared. H3 goes to H3, H2 over z plus H1 over z squared plus 1 over z cube, and then gives a result. Okay? So we are ready for the description. Of the generating function. So what is my, I repeat the goal. The goal is I take an n times n matrix. Suppose n is finite. Then I take a n by n matrix which has 1 in one position and 0 elsewhere. I take a polynomial, an element of that Brn, which is a polynomial in E1, E2, ER, and with some relation. Or, if you like more, since this is the presentation of the cohomology of Grassmannian, take a Schubert cycles, and you want to know what is the product of that Schubert cycle for such a matrix. Because what we are claiming is that then the cohomology of Grassmannian has a structure of a structure of modulo over the Lie algebra of the square matrix. So the description is given by this theorem. This is you must compute W over Z minus W, ZR over WR, gamma Rn is ZW plus Zn. Well, what is gamma Rn? Where gamma Rn ZW is this guy. Now, you see, in this expression, you have a few data. First of all, you see that this expression depends clearly, explicitly from R and N. But look, there is a sigma minus W, sigma bar minus Z, which I defined for you. These are split operator which I explained to you how they explicitly act. And then there is ERW. ERW is 1 minus E1W plus E2W squared. Is that polynomial? Now, the interpretation of ERW, if you remember the previous discussion, is that it is the Chern polynomial of the tautological bundle of the Grassmannian. So I'm saying to you, you take the quotient of the Chern polynomial of the Grassmannian, once GRN, with variable W and variable Z, and the surprise and the very nice things, and this is why I call the sigma. Sigma now is to provocate people working in Schubert calculus, because sigma minus W, sigma bar minus Z are formal power series, and the coefficients are precisely Schubert cycles, and are the Schubert cycles of the Grassmannian of the dual vector space. That's the point. So, in fact, the fact that wedge RVN is isomorphic to the cohomology of the Grassmannian is what allows us to write this formula, because we use heavily Schubert calculus in the way I will try to explain to you. And then the corollary, what is the corollary? The corollary is, okay, but you told us that this formula holds for any n, even n infinity. Then take n going to infinity. And then you see clearly that when n goes to infinity, Zn over Wn goes to 0. what are you saying as? Well, what topology are you using? Well, we could use a natural topology we learned, for instance, in the course of commutative algebra, the completion, to construct the completion of the polynomial ring. But you can also think in a more, in an easier way, because you see, the gamma, what we want to do with the gamma Rn is to apply to a polynomial. This keeps into account the multiplication of Eij for a polynomial. But what is the action of Eij? Is the coefficient of Zi W minus J. And so you see that if Ij are low, the term Zn over Wn is not affecting the coefficient. So when n goes to infinity, it is not affecting the coefficient, the first coefficient. So its contribution is totally negligible, and that's the way we could understand that limit if you don't want to use the completion of the topology you got by completing the polynomial ring. But then the corollary says this, where gamma Rz is now this guy. You see that in gamma Rn, there is again Zn over Wn, but that goes to 0 as well. And then you have this very nice expression, because you see, you have the quotient of the Chern polynomial of the tautological bundle over the Grassmannian, and then do two contributions that, if you believe me, comes from Schubert calculus of the Grassmannian of the dual vector space, if you believe me. This is very nice. And look the colors. The colors are red and blue. Look. The limit for R to infinity of gamma ZW is this one. Look. You see? You take R going to infinity, and this is this part, and this part. And what is X? You didn't introduce X for us. Where X1, X2, and so on is the sequence defined by this relation. You take the formal power series in the Hn, and you define Xi in function of Hn or of the Ei's using this expansion. Okay? And now you can compare with the formula 533. See? That's the proposition gives you the expression when R goes to infinity. And that was the formula 533 of the book by Katz, Reiner, etc. But obtained in a very finite dimensional context. So, idea of the proof, some notation for exterior power. I told you that exterior power are parameterized by partition. Why? Because you know that this is the first element you can think in the wedge RV. B0, wedge B1, wedge BR minus 1. Tell me another basis element. And it takes a different index, which are increasing. So it's the same as the forming with the partition. So BR lambda for me is this expression. Okay? And then it's clear that the R exterior power of Vn, regardless that n is finite or infinite, is that one. And then the proof is this. Take an element of the dual, okay? And recall the contraction operator. I was not supposing the audience remembering this definition, then I give an example. And the example is this. Is in fact, as in some books you can read, is the unique derivation of the exterior algebra of degree -1, such that is the usual dual pairing on the first degree of the exterior algebra. That's, you see, is the derivation. The first applied to E1, but there is some sign to keep into account. And if eta, that's the point. The trace of Eij is equal to the trace of Bi tensor beta j. I told you this. and this, and this. This is the nice expression. This is the same as take bi wedge, beta j contracted with eta. Check, here there is a check for a monomial in a second exterior power. If you do bi wedge, the contraction, you see, I'm contracting beta j with u, and v again, I forgot a j there. But if you make computation, you get this expression. So to compute the trace of Aj is the same as computing bi wedge, bj contracted with eta. Then, you see, I wrote that part in red because this is what we would like to compute. But we were not able to do that. We have to use a trick. I mean, applying the bi wedge bj contracted with eta, we have to write in equivalent way as eta minus, you see that I am switching the operator contraction with wedging. This is because we are working in a certain Clifford algebra, which I'm using some commuting relation of the Clifford algebra. And thus, if I want to write the generating function, you see that is the identity applied to eta minus, I just wrote the generating function of the second line. The first, you see, the first sum is the sum of zi over wj, geometric series. This is is the expansion of w over w minus z, minus, and there is this guy, sigma minus w transpose sigma plus z by b0 wedge eta. What are these? Because this is nothing smart. It's just to write, I have an operator, sigma plus z. Applied to b0 is b0 plus b1z plus b2z square and so on, okay? So I decided to write in that way. Why not? But what I can do about that? But the problem is that sigma plus z and sigma minus w are the unique. Now you see there is something changing because I'm not using just one exterior power, but all the exterior algebra. These are the unique Hasse-Schmidt derivation on wedge Vn such that, now that is the book by Parent and myself, is Springer IMPA lecture notes. It's not just to do improper advertising, just for propaganda. It's just to say that, unfortunately, this is the only reference. Because the new thing, the really new thing in all this argument is this notion of Hasse-Schmidt derivation, which means the following. You see, Hasse-Schmidt, it means that I know how sigma plus minus act on bi. It's just the shift. For instance, sigma 3 applied to b2 is b5. Sigma minus 1 applied to b4 is b3. Just shift forward or backward. And I am asking that they are ring homomorphism. I mean that it respects the operation, the wedge operation of the exterior algebra. That's the nice thing. And then you see that those formula now are not so, are not so, wow, I'm missing, I would have said in Italian, inerti, no? But I'm sorry. I mean, this formula can be used. Here there are, this slide I'm telling you that there exists also the inverse Schubert derivation. What is the inverse Schubert derivation? Sigma plus z is a formal power series. its first coefficient is 1. It's invertible. So you invert in the ring of formal power series, and you get a new formal power series, which turns out to be a Schubert derivation. That is some behavior on the first degree of the exterior algebra, but it is also a homomorphism on the exterior algebra. It is respecting the wedge product. And then, thanks to Giambelli formula, this formula comes from my paper in 2005, when I introduced for the first time this Asser-Schmidt derivation over an exterior algebra. It says that look, the element of the exterior algebra corresponding to partition lambda, you can got by taking the element associated to the partition 0 and just acting with a sure determinants where the entries now are the operator sigma I, which these sigma i's are called sigma because these are the Schubert cycles of the Grassmannian. They are not as if they were the Schubert cycle. They are exactly the Schubert cycle. That's the important thing. And hence, then the R exterior power may be seen as a module over BRN, and the module is, I take EI multiplied by eta, and what is the multiplication? I just apply sigma bar I. You forgot the definition, but that is not important at this point. And then you multiply HI for eta, that is, there is no bar. In the second formula, there is no bar. And so what we are saying is that the EI and the HI are the eigenvalues of this Schubert derivation, whose coefficients are Schubert cycles, are either Chern class of the tautological bundle or Chern classes of the universal quotient bundle. In the finite case, so if the n goes to infinity, we are in a sense doing a Schubert calculus for infinite Grassmannian. Moreover, we have, so this formula, that the definition that sigma minus z applied to the sure polynomial is the same as applying sigma minus z, which is a Schubert derivation, and then I take the coefficient. And then these expressions are compatible with the definition I gave you. Well, there is a case step. I told you that it was the idea of proof could be slightly technical, but what should be kept from this talk, if it should be kept, is that to reach this formula, the expression of this generating series, you need Schubert calculus, and not Schubert calculus of just one Grassmannian, because I am using the exterior algebra. If you believe that each exterior power is isomorphic to the homology of one Grassmannian, working on the exterior algebra means that I'm working on all Grassmannian at once, as people do with the Hilbert schemes of points, as people do with moduli space of curves to study intersection theory a la Witt and Kontsevich. Okay, you can do the same with Grassmannian. If you do this, work with all Grassmannian at once, you get that formula, you have an interpretation of the date Jimbo, Miva, Kashivara. So the case step is the integration by parts. Look, you see that sigma minus W transpose, whatever it is, probably you are lost now, but the point is that you can factorize, you see? You factorize and then some extra term appears inside the parentheses. Well, and then this technique, I told you that there would have been appeared some technique, and the nice thing is that sigma minus W, sigma plus Z are not commutative. They do not commute. Okay? You can think to the Schubert cycles of, let's say, the Chern polynomial of the Grassmannian of the dual vector space and the Chern polynomial of the Grassmannian, they do not commute. They do not commute, and there is this commuting relation. This is the term W over W minus Z. And then substituting in the formula star star and using the isomorphism BRN, wedge RVN I told you about, you get the results. Believe us for today. So, thank you. Proud to be ALGA. Thank you.